Okay, this is our team for Lab 9. This is Zhipeng.
And this is Fei.
This is 林金花.
Okay, so in milestone one, so we want to design and implement a Q learning-based reinforcement learning agent that learns to navigate to a randomly generated maze. The agent starts at the top left corner and must reach the bottom right goal. Um, so this is our um, this is our goals. And also in the meanwhile we should avoiding the walls and the boundaries. So and this task will demonstrate the core concept of reinforcement learning and including the interaction between the environment and the agent. So and let me repeat it, the environment design. And so our environment is defined um, in the maze environment class. So the maze is represented as a multiple M grid with 10% of cell randomly turned into the walls. So each cell can be 0, 1, 2, which 0 means empty, 1 means wall, and 2 means goal. So the starting state is zero point 0, and the goal is n minus 1 and m minus 1. And the agent can take four action up, down, left, and right. So, so when the agent takes the action, moving into the wall or outside the grid, the result in will staying in place and receiving minus 10 penalties. And each normal move will give an negative one step cost. But when we reach the goal, it will yield a 100 positive reward. So the reward structure will encourage the efficient path while penalizing the invalid move. And for the Q learning algorithm, so we have a class called a Q learning agent. So this class implements the standard Q learning algorithms. So each action um, state action pair will store a Q learning that estimate the um, expected reward. And the rules will uh, in here. So we have transferred the formula into the code. So the A, the S, let me see, the S, uh, the S is the state, and S next is the next state, and which the A is the learning rate, and the R is the discount factors. So at each step, the agent choices or action using the greedy policy, where the probability will take a random actions, and where uh, the 1 minus P probability will choose the best action from the two tables. And to balance the learning, the P will decay linearly from zero point 0.9 to zero point 0.1 over like the first 100 episodes. So, in addition, every 5 episodes, the agent is forced to take 3 random actions to ensure diverse exploration early in the training. And in the training evaluation part, the training group will run for 1,000 episodes. In each episode, we will recite the environment and let the agents interact until it's reached the goal or the maximum number of steps. And then we will update the Q values at every step. And finally, we'll store the total rewards of the episode. And then after training, we evaluate the learned policy with 100 test episodes where the p equals to 0. I think that's the all of the for the results. We didn't run this time, but the result is around like 17 to 18 range. Yeah, I think it's all for the milestone 1, and then we'll pass to the milestone 2.
Okay, thank you, Zhipeng. Let me share my screen first. Okay, so hi everyone. Now we will move on to milestone 2, where we explore a more advanced technique, accelerating our agent's learning process by training it with historical gameplay data. So the core idea here is simple. Instead of starting our agent from a complete blank state like in milestone 1, we are going to give it a head start. So how did we implement this? Our approach involved three key steps. First is generate historical data. So we first run basic agent to generate a data set of successful and efficient mice solutions. And second, pre-train with a warm start. We use this data set to pre-initialize our new agent's Q table, giving it a viable peer-read knowledge before it started exploring its own. Second is parallelized self-play. So finally, we trained the new agent using two custom rules. One rule is that higher learning rate was applied to states from the historical data to reinforce good pace. Another one is the initial exploration rate was lowered to 0.5 to leverage the agent's new knowledge. So let's look at how this was implemented in the code. So the first key function is generate historical data. Here you can say we create a template agent. It is trained for 5 episodes, and after each successful run, we check at this line whether the number of stamps taken was less than our successful stamp cap of 400. If it was, we add the entire path to our dataset. And this function returns the high quality study material for our main agent. So next step is to use this data. This happens in the pre-initialized Q table from history. This function is enabled by a small change in agent's update method. So first, we call the set period states. This tells the agent which states are special and deserve a higher learning rate. Then we loop through our historical data set and call agent updates for each step. And another one for upstate is right here. Inside the update function is the core of prioritized learning. This line alpha equals to self alpha map get dynamically checks if the current state is one of our priority states. If it is, alpha is set to point 15. Otherwise, it remains to the default point 1. This ensures our agent continues to learn faster from the proven pace. So let's run the code to see what happens. Okay, so first, this will generate two page. Let's delete first and see the. We can delete it first, and then rerun the math2, and it will generate two pictures as it shows here. So this paragraph illustrates the milestone 2 agent, starting with a strong performance due to pre-training, shows a clear and steady improvement in total rewards over 500 episodes despite some episode-to-episode volatility. So and another picture compares the training of milestone 1 agent in blue against our milestone 2 agent in green. So the difference is striking. This green line representing milestone 2 shows up to high stable rewards almost immediately compared to milestone 1, and it stays there. In contrast, the blue line for milestone 1 takes nearly 400 apple ties to stop fluctuating and converge to an optimal policy. This shows our warm start strategy significantly improve the convergence speed. But interestedly, while the learning speed was much faster, the final performance was nearly identical after 200 apple size. In our test on 15 times 15 mice, both agents achieved a 100% successful rate and averaged about 28 steps to the goal. This tells us that after a mice of this size, the premier benefit of using historical data is efficient. So to conclude the milestone 2, we successfully demonstrated the pre-initializing a Q table with historical data is a highly effective technique. This sets the stage for milestone 3, where we will explore if a neutral network can learn even more efficiently. So let's pass to milestone 3 to my teammate.
Okay, thank you. Let me share my screen. Can you see that? Okay. In milestone 3, we upgraded the maze agent from milestone 1 and 2 to use deep Q learning. And before, we used the Q table to store values for every state and action. But when the maze becomes large, that table grows huge and learning becomes slow. So now we use the neural network TQN to predict Q values. This makes the agent faster and more general and can handle more complex mazes. So the process is the agent sees the maze, it picks an action and moves, then gets reward and learns from experience and repeats. We can see the maze environment is the same as milestone 1 and multiply M. And according to the file, the DQN class defines a neural network. The input is one hot vector of length and multiply M, meaning which cell the agent is. And there are 2 hidden layers, each with 64 neurons using ReLU activation. And the dropout 0.3 is added after the first layer to prevent overfitting. And the output are for 4 Q values for 4 possible moves, up, down, left, and right. And the DQN agent. So the agent learns through 4 main techniques. The first is epsilon greedy strategy. We can see it starts exploring randomly the epsilon equals to 0.9 and slowly becomes more confident epsilon to 0.1. So we use CPU store the maze environment and device, and each cell is a state. The action is 4. And we built 2 identical networks. The target model is initialized with the same weights. And this is the optimizer and the Huber laws. The next one is replay buffer. So it saves 1,000 past experiences and learns from them randomly. The third one is Huber laws. And our target network is a copy of the main network that updates slowly and helps keeping learning stable. And this computes epsilon for a given episode, and the 1 hot is the input. It encodes a maze cell into a 1 hot vector of length. And in transaction, it implements the epsilon gradient policy. So if a random number is smaller than epsilon, it pick a random action. And otherwise, it uses a model to predict Q and choose the max action. Next, we move to the train. And during training, the agent repeats this loop. Get the current state and use the greedy strategy to choose an action, move and get a reward, and then save the experience. And then sample a batch and train the network. After each episode, the target network is updated unless it's a frozen episode. And this is the evaluate part. We evaluate the train agent 100 times with epsilon 0, and each run resets the maze and lets the agent choose the max Q. If the goal is reached, we record success and step count. And finally, we can compute the success rate and the average steps. So we run this file and after 1,000 episodes, the DQN agent learns to reach the goal in about 28 steps, almost the same as M1, milestone 1 and milestone 2. But we can see the training curve is smoother and becomes stable much earlier. And that means the agent learns more efficiently and doesn't fluctuate as much as the previous Q-learning models. And because the running time is I use CPU, so it may takes a little bit more time. So I won't show in there. Okay. This is the end.
Okay, thank you. That's all for our lab 6, lab 9.
Thank you.
Bye.